everyone, my name is Joel Dunay and this is my official unofficial network state exam solution. And now it's about the 24th topic, which is about redundant switch topologies. It's mainly or similar than to the previous one. Redundancy in the access and distribution layer consequences. So I believe I have spoken a lot about the access and distribution layer. Access is the layer where we are having hosts and switches, and the distribution layer is where we are having routing. So of course why it is good? Because if we are having redundancy, that means we are the physical redundancy, that means we are having, for example, multiple switches, multiple cables, multiple routers. So the really big advantage is the availability, because if something will happen with a link, then the traffic will still go to its desired destination, because there is another logical path from the source to the destination. So that's the basic consequences of the physical, is that providing high availability, and if something will happen, then the network will not will not be destroyed because of a single error, but it can operate after an error as well. So that's the advantage. Of course, if we are having more routers, that will help us to having more logical paths to a destination. Issues caused by redundant switch topologies. So it's quite important that we are talking now about layer 2 switches, so that's important. Imagine that we have 3 switches, and we have a host here, and a host here. These switches are connected in this direction, and from this switch the hosts are connected, and here is the other host. So now it's about the issues caused by redundant switch topologies. As I said, switches are working at layer 2, when they don't have routing tables like the layer 3 routers, therefore they are using their MAC table. So imagine a simple network where we are simply having like this, we are having switches, and imagine that he will be, or she will be, the first host, the second, and the third. And imagine that from one we would like to send a message to third. So what can happen? The message or the frame will be or get received by this switch. It will send out a broadcast to this one and to this one. And imagine that this switch and this switch somehow both knows the destination of 3. So what's going to happen? Both of them are going to send a unicast message to the destination. Of course, this is a problem because they cannot handle multiple unicast messages simultaneously, so that's a problem. The other problem that is described here is the broadcast storm, and the broadcast storm is somehow connected with the MAC table instability. Because imagine the other scenario where the broadcast message from this switch is going out on all its ports, then this switch will receive it, it will send out a broadcast to there, for example, and the broadcast to there. This will receive, will send out a broadcast to there. That's not good there. That's skip that one. So what's going to happen? That they will starting to send broadcasts for each other simultaneously, because there will be a loop. And what's going to happen? Their MAC table will always be updated. That will be called as MAC table instability. And what's going to happen also is as their MAC table, for example, will be updated, then they can run out of resources, and that's called the broadcast storm, which means denial of service, so the switches will not operate, and a message cannot be forwarded from 1 to 3, from host 1 to host 3. So let's go back to our previous example, previous scenario. And of course now the solution is the spanning tree protocol, because the spanning tree protocol ensures that by implementing it we will get a loop-free network. That means there will be only one logical path from a source to a destination. And the STP is quite, the spanning tree protocol is quite easy because it's using root bridge and election process to decide on which or where will be the path on which the path will be taken from a source to a destination. So how this election is working, if I remember well, these switches are sending BPDU traffic within each other. So they are sending this traffic because they have, if I remember well, bid or yeah, it's bid or bod maybe, I don't know. I believe it's bid. So they are sending these bid traffic. I mean, within the BPDU there is this bid traffic, if I remember well, or it has another name, I don't know. But within the BPDU it sends a traffic that where these switches will include their original router ID, their root bridge ID, and the cost, I believe the cost. So what's going to happen? The election is based on the root bridge ID, so we don't really care their actual ID. The root bridge ID is important because imagine that this will be 1, 2, 3. Of course it's not a good example because it's not 1, 2, 3 in real life, but it's like 1000 or 10,000, I don't know. So let's imagine 1, 2, 3, and what's going to happen? This will send out its BPDU to this to its available links. These are going to send out their BPDUs as well, and they will simply update their router ID. So if it will receive a BPDU, it will update its router ID that, hey, my router ID is 3, but his router ID is 1, so I'm going to update my router ID with 1. And the exact other thing will happen here. It will realize that there is another router ID where root bridge ID which is smaller than mine, so the other will be the root bridge. So the root bridge election is based on the root bridge ID. And what's going to happen? They share this BPDU, they set up a root bridge, so the traffic will go through on the root bridge, but we still have to ensure that there will be no loops in the network. So what's going to happen? We are going to work with the ports, because I'm going to visualize that the red one will be the root bridge. So the ports will be visualized by purple. All the ports that are connected to the root bridge are called as root ports. All the I'm going to visualize it with blue. All the ports that are connected, I mean all the ports that are on the root bridge, and of course they cannot be root ports, so all the root bridge ports are designated ports, which are non-root ports which are still able to forward traffic. So what's going to happen now? We still have loop in the network. So we have a third one, we have the alternate or the blocked port. So I'm going to visualize it with red. We put, for example, here red block ports, and on the other side there will be a designated port, because it's not a root port, it's not connected to the root bridge, but it can still send traffic. So what's going to happen? I'm going to visualize it. If the traffic will go to this direction, then the traffic will be passed here, but the traffic will be discarded here. So this will ensure that when the traffic will go to this direction, this will be discarded, therefore there will be only one logical path from source 1 to destination 3, therefore we made a network loop, a loop-free network. And of course I believe this is called as an alternate port, so I believe if something will happen with this cable, then this will be activated and the traffic can go through this direction. So basically, that's all about the spanning tree protocols. The important stuff here is the root bridge. The election process is based on the root bridge ID, and the ports, because the ports are ensures that how the logical path will be created. So what do I have to talk about anything else? The role of the root bridge, election, state of the ports, port roles and transition. So that's all. I've talked about everything about this topic. You have to draw up this example and you have to tell how this simple example works. Of course, you remember that if we don't have STP, then the traffic would go in an endless loop, for example. That's why we have to use STP in order to make it loop free. So that's all about this topic, and again, if I said something wrong, then I didn't really care, and don't forget to subscribe.